The relevant types are defined in package Plutus -ledger -API, and the modules of interest are plutus.v1.ledger.value, and then special support for ADA in plutus.v1.ledger.ada. Let's look at the value module first. A value is defined as a map from currency symbols to maps from token names to integers, which sounds a bit weird and complicated. So the first thing to note is that each native token, including ADA, is identified by two pieces of data, a currency symbol and a token name. If we go to the top of the module, we see a currency symbol is just a new type wrapper around a built-in byte string. The same is true for token name. So token name is also just a new type wrapper around a built-in byte string. And as I said, the combination of the two, a currency symbol and a token name, so these two byte strings define a native token or coin. And there is also a type for this actually. That's called asset class, another new type, and that's a wrapper around the pair of currency symbol and token name. So ADA or Loveless will be one asset class, and custom native tokens will be other asset classes. And this map from currency symbol to map token names to integers is equivalent to a map from asset classes to integers, which means that a value just says how many units of each asset class are contained in it. Let's start the REPL and let's import the two relevant modules, Plutus v1 ledger value and Plutus v1 ledger ADA. Let's also activate the overloaded string extension so that we can enter byte strings as literal strings. Incidentally, both currency symbol and token name also implement the isString class. That means we can enter both of those as literal strings as well. Now let's look at some values. Let's start with loveless values. In the ledger.ada module, there is a function called ada symbol, and this is of type currency symbol, and that gives us, not surprisingly, the currency symbol of the ADA asset class, and that's just the empty byte string. And there's similarly a function ADA token, which will give us the token name, and that is also the empty byte string. So taking both symbol, currency symbol, and token name as the empty byte string gives us ADA or loveless. And so how do we construct a value containing just loveless? We have seen that before in the examples. There's a function loveless value of that, given an integer, gives us a value. So for example, to have 123 loveless, we can just do this and we get a value. And by the way, you would never construct a value directly by constructing these maps. Instead, there are always helper functions you can use, one of those being loveless value of. So here we see this map. So the outer map, the map where the keys are currency symbols, has one key, and we don't really see it here. That's because the currency symbol of ADA is just empty currency symbol. Okay, and the value is now a map from token names to integers, and we see this inner map here again has just one key, the empty string, that's the token name of loveless, and finally the value is 123. So this value represents 123 Loveless. One thing we can do with values is we can combine them, add them. So in the case of Loveless, so let's take another example. Loveless value, I don't know, 10. And how do we combine them? Well, it turns out that the value class is an instance of monoid. We briefly mentioned monoids in the last lecture when we talked about the writer monad. So monoids are things that you can combine that have a neutral element called memty, and you can combine two elements to a third element with mapend. But there's also an operator for that that's written like this. That comes from semigroup, which is a superclass of monoid. So doing something like this, I can combine two values. So having the value that represents 123 Loveless and the value representing 10 Loveless, I get a value with 133 Loveless. So how do we create values containing native tokens? There's a very useful function called singleton. And it's a function that takes three arguments: a currency symbol, a token name, and an integer. And that will construct a value consisting of just one asset class given by the currency symbol and the token name, and the integer specifies the amount, how many coins of that asset class are there. So we can construct a value with the native token by now first giving a currency symbol, and as I mentioned before, because we have the overloaded string extension activated, I can just give the currency symbol as a literal string. However, that can't be an arbitrary string. It must be a string representing a hexadecimal value for reasons I'll explain in a minute. So for example, we can do something like A8FF, just as an example. So next comes the token name. That can be an arbitrary byte string. And I can just do whatever, for example, ABC. And now I must give the amount, how many coins, let's say 7. And I indeed get a value. Now we see that in the outer map, the map where the keys are currency symbols, I have one entry, my A8FF. And then the value is an inner map, given in this case only the one token name ABC and the amount 7. Now, of course, I can also combine as before with this mapend operator. So, for example, I can take this and combine it with Loveless value of 42. And let's say I can combine it with another singleton, maybe using the same currency symbol, A8FF, but a different token name, 100. Let's see. So now we get a somewhat more interesting map. So now in the outer map, we have two keys. One has the empty currency symbol, so that's for the Loveless, and then a second entry that has the A8FF currency symbol. In the Loveless case, the inner map, there's only the one token name, the Loveless token name with the value 42. But in the A8FF currency, in the inner map there, we have two entries for the two token names we now have, ABC and XYZ, with amounts 7 and 100 respectively. Let's give this value a name. Let's call it V. And another useful function is, given a value, to extract the amount for a given asset class. That is called value of, and it takes a value and a currency symbol and a token name and gives us the corresponding amount. So if we try that with our V, value of V, and take currency symbol A8FF and as token name, for example, XYZ, then we get the 100 back. If we take ABC, the 7. And if we take a token name that's not contained in the value, ABC lowercase, we get 0. Another useful function is flatten value. That takes a value and returns a list of triples, currency symbol, token name, integer. So as the name suggests, it flattens this map of maps into a flat list of triples. So if we apply this to our example value v, we just get a list with 3 entries. The first 2 are these native tokens, both with the same currency symbol but different token names. And the last entry here is the loveless, the 42 loveless. Now the question, of course, is why? Why do we both need a currency symbol and a token name? Why don't we just use one identifier for an asset class? And why does the currency symbol have to be built from hexadecimal digits and can't be an arbitrary string? And this is where so-called minting policies come in. So the rule is that in general, a transaction can't create or delete tokens. So everything that goes in also comes out. The exception is the fees. So there's always a fee in loveless that has to be paid for each transaction. Fees depend on the size of the transaction in bytes, not in value, and on the scripts that need to be run to validate the transaction. And the script takes more fees if it consumes more memory and if it needs more steps to execute. So, but if that was the whole story, then of course we could never create native tokens. And this is where minting policies come in and where the relevance of the currency symbol comes in. So the reason that the currency symbol, the byte string giving the currency symbol, has to consist of hexadecimal numbers is that that is actually the hash of a script. And this script is called the minting policy. And if we have a transaction where we want to create native tokens or burn them, then for each native token that we try to create or burn, the currency symbol is looked up. That's the hash of a script. So the corresponding script must also be contained in the transaction, and that script is executed along with the other validation scripts. And similar to the validation scripts that we have seen so far that validate inputs, the purpose of these minting scripts is to decide whether this transaction has the right to mint or burn tokens. And ADA actually also fits into this scheme because remember the currency symbol of ADA is just an empty string, which is not the hash of any script. So there is no script that hashes to the empty script. So there is no script that would allow the minting or burning of ADA, which means that ADA can never mint it or burned. All the ADA that exists come from the Genesis block, the Genesis transaction, the very first transaction, and from monetary expansion. So after each epoch, when rewards are paid, part of those rewards come from so-called monetary expansion, where a certain percentage of the remaining reserves gets paid as rewards. And the total amount of ADA in the system is fixed. It can never change. So only these custom native tokens can have custom minting policies and can be created and burned under certain conditions. So we'll look at an example of a minting policy next and see how it works and see that it's very similar to validation scripts but not identical.